Okay, this is section 15.4, and this is called Using Equilibrium Expressions to solve problems. And this is a problem-solving section. Okay, that's what this section is all about, is solving problems. So the example that we're going to look at here is hydrogen gas reacting with iodine gas in a reversible process to form hydrogen iodide. We wouldn't call it hydroiodic acid because it's in the gas phase. It's not aqueous. It would be an acid if it were dissolved in water. And what I'm going to do is I'm going to give you the value of K. Kc is 54.3. This is at a specific temperature, 430 degrees C. As with the previous examples, we don't really need to know the temperature, but K does vary with temperature, so it's given. Now what we're doing here in this example is we're being told the initial concentrations of everything. So these are given, all right? So the initial concentration of H2, I'll put a 0 for initial. Initial concentration of I2, 0. And initial concentration of HI. Okay. And so the initial concentration of H2 is 0.243. By the way, I'm getting these numbers from your textbook, so if you read along in section 15.4, that's where I'm getting these numbers here. If you look at the initial concentration of the I2, it's 0.146. And if you look at the initial concentration of HI is 1.98. Okay, so these are molar. And we're going to ask the first question. There's going to be a series of questions we're going to ask here. Question 1. Is this mixture at equilibrium? Okay. Now the way you can answer that is you take the value of K that you've got. That's known, it's given to us, 54.3. And you calculate Q. And if Q comes out to a number that's really close to 54, then that means you're at equilibrium. So let's write out the expression for Q. Q would be the concentration of HI, remember squared, right, because of the 2, divided by the concentration of H2, divided by the concentration of I2. Coefficients there are 1, so it's to the first power. So now you just put your numbers in. 1.98 molar squared, don't forget to square it, divided by 0.243, divided by 0.146. Okay. So now we do that calculation. So this is the first calculation we're going to do here. 1.98 squared divided by 0.243 divided by 0.146, and you get 110. It's actually 111. That's not at equilibrium, right? That's definitely not anywhere near 54. It's actually, it turns out it's not that far off from 54, but it's not 54. If you got 55, yeah, you're at equilibrium. If you got 53, sure. But if you're at 111, that's 2 times the 54. So that can't be at equilibrium. So what we're going to do is we're going to make the following claim. We're not at equilibrium. And the reason for that is because Q is not equal to K. Okay, that's the key there. If they're not equal, you're not at equilibrium. So now what I'm going to do, I'm going to erase all of this, or much of this, to give us some room to work with. I'm going to leave the chemical equation there so that you can see what we're going to do. We know that Q is not equal to K. Okay, so I'm going to write these numbers in. 0.243 0.243, 0.146, and 1.98. Okay, and I'm going to call this our initial. I'm going to put a little square there, I for initial. Now what I'm going to do is I'm going to make the following claim down here. If Q is less than K, the reaction goes in this direction, to the right, toward products. If Q is greater than K, the reaction goes the other direction, to the left, toward reactants. Okay, so what's going to happen here? Q was 111, so Q is greater than K. So that's the second case down here. So here's what's going to happen. We're going to represent this as a change. So this is step 2. We did the initial here. Now I'm going to do a change. And the way we do this is if it's going to the left, that means H2 is going to get bigger and I2 is going to get bigger. So I'm going to write plus signs to indicate they're bigger. They're going to get bigger at the expense of HI. HI is going to break up into I2 and H2, so it's going to be minus. It's going to get smaller. The change is decreasing for HI. Then what I'm going to do is I'm just going to drop the coefficients down. The coefficient for H2 is a 1. The coefficient for I2 is a 1. And the coefficient for HI is a 2. Then I'm going to use a variable. And the variable that I'm going to use is an X. Okay, so the change that's going to happen is HI is going to go down by 2x, so minus 2x. HI is going to go up by 1x, and H2 is going to go up by 1x. H2 and I2 do the same thing. Then I'm going to do what's called equilibrium. I'm just going to add these two terms together for each one of them. So 1.98 minus 2x. 0.146 plus 2x. 0.243 plus x. Oops, sorry, I put 2x here. There's only 1x. That's a mistake. Sorry. Plus x, right? So 1x is the same as x. So here's our three terms. Okay. And so this is an equilibrium problem. Now what I'm going to do is I'm going to take those and I'm going to say, wait a minute, this is at equilibrium. So that means we can substitute these directly back into our equilibrium expression. Equilibrium would be the concentration of HI squared, so that would be 1.98 minus 2x squared, right? That's HI squared, divided by concentration of H2, which is 0.243 plus x, divided by 0.146 plus x. Okay? So that would be the expression for the equilibrium constant, which we know is equal to 54.3. So here's what we do with this, and I'm not going to show this in this lecture, but you'll look at it in sample problems. We're going to solve for x algebraically using algebra. And if we solve for x, what that does is the following. At equilibrium, the concentration of HI is 1.98 minus 2x. So if we solve for x, we can calculate what the concentration of HI at equilibrium is just by plugging that in. So let's say that x was 0.01. We would just take 1.98 minus 2 times 0.01. We can also find the concentration of I2 at equilibrium just by taking 0.146 and adding it to x, so 1.46 plus 0.01. And we could do the same thing with H2. 0.243 plus x. So we just 0.243 plus 0.01, whatever x turns out to be. And then that will give us our equilibrium concentrations. Okay, so the idea here, this is really, take a look at the section title again, using equilibrium expressions to solve problems. This is the solving the problem point. So let me review it just so that you can sort of see what the approach is. And then, quite frankly, it really isn't very real until you actually do the problems. But step one, you calculate Q. Step two, you compare Q to K. And then part A would be if Q is less than K, then the reaction goes this direction. So you get plus x on the right side and minus x on the left. If QC is greater than K, which is what we just saw, then that means the reaction goes this way to the left. So you get plus x on this side and minus x on that side. Now, the trivial case is that it turns out it's just equal to K, then that means it's already at equilibrium and there's nothing to solve for. So once you figure that out, you set up the ICE table, initial change equilibrium. Okay, so you can have plus x's and minus x's. Remember, the coefficients get dropped down too. For, use algebra to solve for x. And then plug that value in to find the equilibrium concentrations. This is the power of the physical sciences, this power of science, is that essentially what we're doing is we're making a prediction of the future. We're putting in initial concentrations for a known chemical equation, and from arithmetic and our understanding of the law of mass action, we are predicting the equilibrium concentrations. We are predicting the future.